This is the mean value theorem. It is a theorem about a function that is continuous from a to b and differentiable from a to b. The round parentheses here means it does not, the function does not have to have a derivative at a or at b, but it has to have a derivative at every number between a and b. So for a continuous and differentiable function on some interval, there exists at least one number in the interval such that this is true. F prime of c, that means the derivative of the function at c, is equal to f of b minus f of a over b minus a. Please pause the video to write all of this down. The important mean value theorem. Then after you've written it down, you'll see a picture of the theorem. It looks like this. So any function that is continuous, that means there's no holes in it and no vertical asymptotes. Differentiable means it's smooth, no sharp turns. Pick any point on this curve. Say it's the point A, f of a, because it's a point on the function y equals f of x. Pick some other point whose coordinates are b, f of b. The line through these 2 points, that line right there, would have this slope, the change in y over the change in x. All of this red just means the slope of that line. The theorem says there's at least one point between a and b. There's at least one point where the derivative of the function at that number, c, some number between a and b, is equal to the slope of that red line. There's at least one place where the derivative, that means the slope of the tangent line, is equal to the slope of the line, of the red line. Equal slope means these lines are parallel, the red line and the green line. The red line is called a secant line because it crosses 2 points on the curve. The green line is called the tangent line. The theorem can be stated like this. There's at least one number c, or one point in the interval, where the tangent line is parallel to the secant line, because equal slopes means the lines are parallel. On page 192, exercise 16, f of x equals x to the 2/3. There's the interval 0 to 1. The question is, and we're only doing part B in this exercise, is to find the value of c in the interval 0 to 1. Notice these are round, even though they're square up here. Find the value of c in the interval 0 to 1 that satisfies the mean value theorem. We're going to say MVT, mean value theorem. To answer this question, we're going to find the derivative of the function, which, because there's a 1 here, the derivative is 2/3 times 1 times x raised to this exponent minus 1. 2/3 minus 3/3 is negative 1/3. So there's the derivative of the given function. F prime of c means replace any x with a c. So the mean value theorem says there's at least one number in the interval 0 to 1 that satisfies this equation. F prime of C equals f of B minus f of A all over B minus A. In this exercise that we're doing, f prime of C is right there. It's 2/3 C to the negative 1/3. The B and the A are 0 and 1. F of B minus f of A means in this exercise it's f of 1 minus f of 0 over B minus A. That means 1 minus 0. The left side of this equal sign could be rewritten as 2 over 3 C to the positive 1/2. I mean positive 1/3, sorry. And f of 1, according to what's given, f of 1 is 1 to the 2/3. F of 0 means 0 to the 2/3. So in this exercise, the left side of the equation in this case is 2 over 3 C to the positive 1/3. F of 1 is 1. F of 0 is 0. So this entire left side, or the entire right side of the equation is just 1. I'm going to write over 1 because now we're going to cross multiply. We're going to say this denominator times 1 equals this numerator times 1. Divide both sides by 3. And now we have, I'm going to rewrite this, C to the 1/3 equals 2/3, because I want to tell you what we do now is raise both sides to the 3rd power. Because C to the 1/3 to the 3rd is just C. And whatever we do to one side of the equal sign, we do the same thing to the other side. 2/3 to the 3rd, 2 times 2 times 2, over 3 times 3 times 3. So that's the number, 8/27, that's in the interval 0 to 1, that satisfies the mean value theorem. This sentence is the conclusion, this equation is the conclusion of the mean value theorem. Number 8 on page 192 says, y equals x to the 4th minus 10x to the 2nd plus 9. And what we're going to do without a calculator is find the local extrema, intervals on which the function is increasing, and intervals on which the function is decreasing. So this is given. We calculate y prime, 4x to the 3rd minus 20x to the 1st. We're going to try to find when the derivative that we just got is equal to 0. We can factor 4x out. 4x times x squared minus 5 equals 0. So the derivative of the given function equals 0 when x is 0 and when x is plus or minus the square root of 5. These numbers that make the derivative 0 are called critical values. Values of x for which the derivative is equal to 0 are called critical values. Now we're going to write this. F prime, and x. On this line, we're going to locate the critical values, which are 0, square root of 5, and negative square root of 5. 0 is a critical value, the square root of 5 is a critical value, and negative square root of 5 is a critical value. The reason these are critical values, f prime is 0 for these x values. Now we're going to pick any number before negative radical 5. Let's say we use negative 10 and plug it into f prime. I think perhaps I should have called these y and y prime instead of, let me change these. This is y prime and this is y. So we're picking a number over here like negative 10, and we're going to plug the number we choose into the derivative, which has the red circle around it. So if I'm using negative 10. If I square that, I get 100, subtract 5, I get a positive number. And then I'm putting negative 10 here also. That means I'd have a positive times a negative times that positive 4. These are all multiplied in the red circle, the red ring. Multiply two positives and a negative, you get a negative. Pick a number in here in this interval between negative radical 5 and 0, like negative 1. Negative 1 squared is 1. And then subtract 5, you get a negative. A negative times a negative times a positive is where the x is. I'm putting negative 1. Multiply these, we get a positive. Pick a number between 0 and the square root of 5, like 1. For example, pick a number in here like 1. 1 squared minus 5 is a negative, times a positive, times that positive 4. Multiply two positives and a negative, we get a negative. Pick a number bigger than the square root of 5. Say, for example, 10. 10 squared minus 5 is a positive. For the x's, we're putting 10, so that would be a positive. The 4 is a positive. Multiply 3 positives and we get a positive. So now here's what we know about y. We now know that y is decreasing, then increasing, then decreasing, then increasing. Whenever the derivative is negative, the derivative of a function is negative, the function is decreasing. In other words, something with negative slope goes like this. If the derivative of a function is positive, that means the function is increasing. In other words, if something has positive slope, it looks like this. So we're going to answer part A by writing this. To find the local extrema, that means local maximum and local minimum. You can tell from this green that here is where there's a maximum. Up, then down. So local maximum is going to have this x coordinate. But we do need the y coordinate. By putting 0 in place of x in here, this is what y equals. When x is 0, y is 9. I can see minimum here because going down then up, down then up. So local minimum, this is the x coordinate. And the y coordinate, we'll get that in a minute. Because there's another minimum here, down then up. So minimum with this x coordinate. So we're going to calculate the y's without a calculator. We know that y is x to the 4th minus 10x squared plus 9. So we're going to take the negative square root of 5 and raise it to the 4th power, minus 10 times negative square root of 5 to the 2nd power, and then add 9. squaring negative radical 5, you get positive 5. Negative radical 5 times itself 4 times is going to be 5 times 5. I know I left the negatives out, but a negative to the 4th power is positive anyway. So we have 25 minus 50 plus 9. That's negative 25 plus 9. That's negative 16. You should realize that if I use positive radical 5 instead of negative radical 5, this still comes out to be negative 16. So there's the answer to part A. Find the local extrema. Here's our answers. Part B, the intervals on which the function is increasing. The intervals on which the function is increasing. I'll just look back up here and see this green increasing. We're going to say from negative radical 5 to 0. From this x up to this x. And we will use square brackets. We'll discuss the reason in class. That's not the only interval we're increasing. We also have here, increasing here. When I say here, I mean from radical 5 all the way to infinity. And I have a mistake because I'm supposed to use a square bracket. Radical 5 to infinity always gets round. That's the answer to part B. Those are the intervals where the function is increasing. I just look for where the green arrows were pointing up, increasing. Part C, intervals on which the function is decreasing. So look back up here. Here's decreasing right here. When I say here, I mean from negative infinity up to this x, from the x value of negative infinity up to this x, negative radical 5. And negative infinity always gets rounded. And ironically, we put square on this also. We say that at negative radical 5, the function is doing two things at once, multitasking. The function is increasing and decreasing at the same time at the number negative radical 5. So these all get square brackets, except for the infinities. Also decreasing here. When I say here, I mean from this x to this x, this interval, 0 to radical 5. Please put square brackets around everything except the infinities. So these are intervals. Intervals means the x values. The extreme values are really the y values. Local maximum is 9. I'm also giving the x, but they really just want the 9. And the local minimum is negative 16. It occurs at two different places.